as an example of equilibrium for a system of rigid bodies, let's look at the following case. So I have a set of tongs, ADF and BCE, that are connected together with a spreader bar CD, and they are lifting some kind of metal ingot that weighs 8,000 pounds. Okay, and I'd like to find the force in the spreader bar CD. So this is a system that consists actually of 4 rigid bodies, and if I want to consider the case of equilibrium to find this force, then what I have to make sure of is that each of the 4 bodies is in equilibrium, and that will allow me to determine the answer to my question. So we start with a free body diagram of the system, and what we do is we break apart the whole system rigid body by rigid body. So here are the 4 rigid bodies drawn separated out, the 2 tong arms, the spreader bar, and the ingot. And now what we do is we add the forces that are acting on each body. So for instance, one of the tong arms, the ADF, is subjected to a vertical force at A. There's going to be a horizontal force at D due to the spreader bar, and then there's 2 forces where the tong grips the ingot, so in the Y and the X direction. And I can go ahead and now put in the forces on the spreader bar, and I know by action equals reaction that those are going to be of magnitude S. And it's a 2-force member, so they're going to be in the horizontal direction. So I can take advantage of that already. Okay. If I go to the other tong arm, I have the force at B. I have the reaction force at C due to the spreader bar, so that's still S. And then I have the 2 forces where the tong grips the ingot, EX and EY. And then lastly, I have my forces on my ingot. There's the gravitational force of 8,000 pounds in the center. And then I have the equal and opposite reaction forces from the tong arms, EX, EY, FX, FY. So you'll notice I've left the magnitudes the same, but just drawn the arrows going in the opposite direction as I have on the tongs. Okay. Now what I need the total resultant force and the total resultant moment to equal 0 for each of the 4 rigid bodies. Okay, and I can use this to determine the force in the spreader bar. So the unknown again that I'm interested in is the spreader bar force S, and I have equilibrium of each rigid body to help me try and determine what S is. Okay, so we can start with the ingot, and if I sum the forces in the ingot in the vertical direction, I have Fy plus Ey equals 8. In the horizontal direction, I find that Ex has to equal Fx. And I can sum the moments about any convenient point, so I pick the point E, which gives me 8 times 55 over 2, so that's the lever arm from the center, minus Fy times 55, so that's the lever arm from Y to E, equals 0. So I can use these equations already to find out that the force Y at E and F are 4 kips, and that the force in the X direction at E and F are equal to each other. If we now consider the tongs, we can look at force equilibrium in the vertical and horizontal directions, and then moment equilibrium also. And so starting with force equilibrium in the vertical direction, we see that By equals Ey and Ay equals Fy, and using our results from above, we see that Ay equals By is equal to 4 kips. We can now look at force equilibrium in the horizontal direction, and then we see that the force in the spreader bar is equal to both minus Ex and minus Fy. And now if we look at moment equilibrium and we do that about point C, we find that Ex times its lever arm, which is 55, plus Ey times its lever arm, 5, and By times its lever arm, which is 59, all have to equal to 0 for equilibrium. And plugging in our results from above for both Ey and By, we find out then that the horizontal force on the tongs, Ex, is equal to minus 4.66 kips, and this then implies that the horizontal force, or the force in the spreader bar, is 4.66 kips, and it's positive in magnitude, so that tells us that the spreader bar is in tension in this problem. And that was the original question, is to find out that force.